We've been talking about nuclear physics and radioactivity, and that was getting into the nucleus. Now we're getting into the realm of even smaller yet of quantum mechanics. And what I want you to recognize, you guys, is that in the early 1900s, there were two major revolutions in physics. At the end of the 1800s, physicists pretty much thought they were done with doing physics. We pretty much figured out, we'd calculated everything that needed to be calculated. We could do whatever we needed to do. We just kind of had to refine some things. And then physics would basically become like a history class. But two things happened in the 1900s that changed all that. Relativity and quantum mechanics. And these happened in very different ways. Relativity happened from one man sitting by himself thinking a whole bunch. And pretty much happened overnight, publishing a paper on special relativity in 1905, and Einstein changed the world. He published a second paper on general relativity about 8 years later, and again changed the world. Quantum mechanics was very different. Quantum mechanics was happening simultaneously, but took about 30 years to fully be figured out, and it took many, many different scientists to contribute to how it works. So even though these two revolutions happened, they happened very differently on different time scales. All right, so let's go way back to the time of Democritus. We talked about this briefly in an introduction when I introduced nuclear physics to you, but again, remember Democritus is the guy that came up with the concept of the atom, from the Greek word atomos, which means that which cannot be cut, or that which cannot be divided. So his theory was, and this was a long time ago, his theory was that there is a small fundamental unit of things that can no longer be broken down. So like you take a block of gold and you break it down into smaller and smaller pieces, you would eventually come to a piece of gold that is fundamentally the smallest thing that there is, and he called that an atom. We still call them atoms today. However, we now know that atoms can in fact be broken down even farther. And we keep one branch of physics searches for the fundamental building blocks of matter, and that's particle physics when they get into that and doing all that. In the 1800s, there was a huge revolution in chemistry. That's when chemistry really took hold, and scientists were doing a lot with discovering chemical relationships and elements, and many, many elements were explored and discovered. And that's basically when the periodic table got formed. So we were learning a lot about relationships between atoms and how things work and what the basic atoms of the universe are. Though no one really knew what an atom was at that point. We knew kind of these relationships. We knew how hydrogen and oxygen kind of related to one another and how they were connected in their general abundance, let's say in water or in air. But no one really knew the mechanism or what was going on. At this point, people did not understand protons and neutrons and electrons. They had not been discovered yet. At this point, it was still just the atom. The atom was the fundamental building block, and you had different kinds of atoms that behaved differently, and you could deal with the world that way, and everything was pretty fine. But then in the mid-1800s, 1855, something happened, and this is the main thing that started it all. This is a cathode ray tube, right? Some of you have probably seen this before or heard this before. This is a cathode ray tube sitting here in the front of the classroom as well. And the idea with the cathode ray tube was this. In the mid-1800s, they were starting to be able to create vacuum tubes, containers that had vacuums inside of them, and then you could do cool things with them. This was a special vacuum tube that had a cathode. It had two electrodes, basically, a cathode and anode, which the cathode is positively charged, okay, positively charged. The anode is, oh, sorry, negatively charged, positively charged. That's what it says on the thing. What they discovered with this cathode ray tube is that if they put a really high voltage across these two electrodes, that something would come off of the cathode. Something was coming off of it. It was this glowing stuff, and they didn't know what it was. They didn't know if it was some sort of electromagnetic wave. They didn't know if it was some sort of particle. They didn't know what it was, but they knew it was coming off of it, and people thought, well, that's kind of cool. We're going to start investigating it. And when you put this little cross there, they noticed that there was a shadow that formed on the end here, which led them to believe that whatever it was traveling in straight lines, and they called them cathode rays. They initially called these things cathode rays. They didn't know what they were, but people started investigating them, particularly J.J. Thomson? Is that who was? Yeah, he did a lot of research with it as well. So in 1855, they had perfected cathode vacuum tubes, And again, they found this glow coming from the cathode when high voltage was applied to it. In 1875, they curved the tubes, and what they discovered is it didn't matter what metal the cathode was made of. As long as it was a metal, something would come off of it. Those things would travel in straight lines. If they put magnets around it, they could make them bend. So they knew they were affected by magnetic fields, but they didn't know what they were. Was it some kind of wave, or was it some kind of a particle? And this was argued for about 25 years before it was investigated further and proven to what they were. So there was this classic experiment done in 1897 by J.J. Thomson. And yeah, and this is it. Okay, this is kind of cool. And look at what he did. He created a cathode ray tube, and here's the cathode here. Shoot it at an anode, but the anode has a little slit in it, so some of the cathode rays can go through. Put another anode with the same slit in it so that only the ones that get through are the ones that are traveling straight. Any of them that are kind of at an angle or whatever are not going to get through. So this basically, this apparatus here just assures that the cathode rays are going in a straight line. And then have an electric plate perpendicular to a coil of wire that you can pass electricity through. What do you create when you pass electricity through a coil of wire? A magnetic field. So now you have perpendicular electric and magnetic fields. And you can adjust the magnetic field by adjusting the current in these wires and see what happens. And you can test things, and you can figure out, basically what he was able to figure out is that these things, these cathode rays, were charged, whatever they were, they had electric charge because they felt a force from the magnetic and the electric field. And by altering the strength of them, he was able to calculate their charge to mass ratio. Okay? He was able to calculate their charge to mass ratio and discovered that they were negatively charged objects. Whatever they are, they were negatively charged, and that their charge to mass ratio was incredibly large, like 1,800 times larger than a hydrogen ion. It was 1,800 times bigger than a hydrogen ion. How can that, what must be true if that ratio is that much larger? Either a really small mass or a really large charge. Well, they could measure the charge on it, and Millikan did that with the oil drop experiment, and they discovered that what it is whatever these things are, the mass is incredibly tiny, almost 2,000 times smaller than the mass of a proton. Okay? Well, they knew about J.J. Thomson. Okay. So he used the magnetic electric fields to show that cathode rays were actually these little negatively charged particles. We now call them electrons. So yeah, there you go. All this overlap. Okay, he measured the charge to mass ratio. It was much, much larger. Whoops. Let's go backwards if I can. And it doesn't like me going backwards unless I do this. Okay. So charge to mass ratio was much, much larger than in a hydrogen ion. And when they used different cathodes, when they used different materials for the cathodes, they still got the same charge to mass ratio. So no matter what the metal was that was ejecting these cathode rays, this was the same. So they basically what Thomson was saying was, whatever's coming off of that metal, it's the same thing. Each different kind of metal is giving off the same thing. And it was the first piece of evidence that atoms were not the fundamental building block of matter, that there was something smaller. There was another constituent of matter that made atoms. And it was the discovery of the electron that did this. And that's what's important. Okay? Robert A. Millikan did this oil drop experiment, and he was able to measure the mass. Remember that one where he shot the oil through the electrically charged plates and got it to hover there? And he was able to measure the mass of the electron by doing that. And we found out that electrons are incredibly small little things. That's kind of the summary of everything that I've just been talking about. That atoms are not the fundamental building block. That they are made up of something smaller. And we know that the electrons are part of that, and then later on, I think protons and neutrons came along later, maybe with the gold foil experiment and all that other stuff, and Now, some other things were happening about the same time, and one of the things that was going on was this research into this stuff called black body radiation. Okay. You do need to know about black body radiation. The idea of black body radiation is that anything that has temperature gives off radiation. You guys are giving off radiation right now. You're giving off infrared radiation. The sun, which is hotter, gives off radiation in the visible light and the ultraviolet. But all objects give off radiation. And a black body, by definition, a black body is an object that radiates perfectly, that doesn't hold on to any of its radiation. It emits its radiation perfectly. And any radiation that lands on it, it also absorbs it. That's why we call it a black body. The weird thing is, I'm going to come back to this because I think you should see the picture first. I'll come back to that last slide. If you look at the radiation that an object gives off, it gives it off in a nice curve like this. Okay? Well, like this. And this is a graph of wavelength of the radiation relative to the intensity, how much radiation it gives off at a given wavelength. So if I have a glowing object, it has a certain peak. It has a certain wavelength where it's giving off most of its radiation. But notice that it gives off some radiation at shorter wavelengths and also some radiation at longer wavelengths. Okay, and this is called a black body curve. If I lower the temperature of the object, like from 6,000 Kelvin to 3,000 Kelvin, the peak diminishes and it slides towards longer wavelengths. Okay? You guys are cooler than the sun. You're giving off radiation in the infrared region of the spectrum because the peak wavelength you are emitting is mostly out here. The sun, which is much, much hotter, its peak wavelength is in the visible spectrum, and that's why it appears to glow. Something that's really, really hot will give off in the ultraviolet or even, well, gamma rays actually not from hotness, but kind of get the idea of what black body curves are? A little bit. Scientists were able to measure these curves, to measure the radiation coming off of objects, but they didn't have an explanation for it. They didn't have a mechanism for it. And using classical mechanics, no one could figure it out. A couple of different people tried. Yeah, or no, why you get this curve of radiation. Using classical mechanics, these guys, the Rayleigh-Jeans folks, they came up with a theory using classical physics that explained the curve way down here at long wavelengths, but their theory predicted a different curve at shorter wavelengths. Didn't work. And then this guy, Wien, comes along, and his theory, again using classical mechanics, explained the curve at short wavelengths, but didn't explain it at long wavelengths. No one could explain why objects emit radiation the way they do until Max Planck comes along. And Max Planck says, he came up with a mathematical equation that would explain black body curves. And in order for it to happen, he had to quantize energy. In his equations, if he said energy was not discrete, but energy came in very specific amounts, then he could create a mathematical equation that would explain this black body curve perfectly. Okay? It was the beginning of the idea that energy can come in very specific quantities and not in discrete amounts. He didn't believe it was true. He thought it was just a mathematical trick that allowed him to explain this curve, and the mathematics worked, but he thought the physics was not right, because obviously you should be able to have however much or however little energy you want. You shouldn't be able to, energy shouldn't come in little packets that you can't divide, right? He didn't think that was right. But he was the first one to recognize that relationship. So classical physics just explained that, yeah, if something has temperature, the electrons in it are moving around, they're going to give off radiation. But they couldn't explain the curve. No one could explain this black body curve. Wien's law worked at short wavelengths. The Rayleigh-Jeans theory worked at long wavelengths. Nothing was able to do it until Planck comes along with his quantum theory. All right. So here is Planck's quantum hypothesis. In 1900, he came up with a formula that would explain the black body curve. It fit the curve perfectly. And it worked if he assumed the energy came in quanta, very discrete little packets. You can only have one packet or two packets or three packets. There's no fractions. There's no in between. Okay? And in order for his equation to work, this was the foundational piece. Okay? The quantum of energy is equal to h, which is Planck's constant, times the frequency of that energy, of that radiation. You guys have already used this equation in some of your homework assignments. We haven't really talked much about why, but it is the foundation of quantum mechanics. The energy of a photon, or the energy of a piece of radiation, electromagnetic radiation, is equal to this constant times the frequency. Again, Planck discovered this by looking at a formula that would fit the black body curve. He didn't really believe it. He didn't really believe it, but it worked mathematically. So in this case, n is just a number, a numerical value. So you can only have some whole number multiple of this basic amount of energy. 1 times it, 2, 3, 4, whatever. But you can't have any fractions of it. That's what quantization means. Okay? Max Planck didn't recognize this as being a major revolution because, again, he didn't totally believe it. He knew it worked mathematically, but he just didn't think it could have been right. Einstein was the first person to take it seriously about 5 years later and helped kind of start ushering in this idea. And later, Planck won the Nobel Prize for this in 1918 for discovering this quantization of energy. So here's the main thing, you guys. Here's the beginning of quantum mechanics. And it was the first time that a physical quantity was assumed to be quantized. And in order for Planck's quantum hypothesis to work, energy has to come in very discrete packets, okay? Very discrete amounts. And there is a minimum amount of energy, which is equal to h times f. And you can only have some whole number multiple of that. And molecular vibrations, when things oscillate, molecules oscillate, it's not continuous, but it's also discrete. So those are kind of the beginnings of this whole idea of quantum mechanics. Now, from this, a lot of things grew out of it, and this whole theory of how we explain the world of the incredibly small. That's when quantum mechanics really works. When you get down on really small scales, you have to start dealing with quantum mechanics. It does still work, but it becomes less obvious. What's that? Gravity does not work on very small scales. That's definitely something. Okay, so one of the things that you're going to read about in your homework assignment is this. Einstein's contribution to quantum mechanics, which basically is based on the photon theory of light. And in 1905, Einstein said, well, hey, if energy comes in discrete little packets, then maybe light does too. Maybe light should come in little packets. He gave them a name, called them photons. And he said each photon should have a discrete amount of energy, hf. And this is a classical argument because light has always been argued. Is it a particle or is it a wave? Is it a particle or is it a wave? And there's all these experiments that had been done to prove that light was a wave. Do you guys remember any of the experiments that showed that light was a wave? Okay, the double slit experiment with diffraction, the fact that it diffracts and refracts and does all this is evidence that light was a wave. But Einstein said, you know what, if quantum mechanics is working, if what Planck says is true, then maybe light comes also as little particles, little discrete little packets, rather than being, an infinitely changeable thing. Maybe it is quantized as well. And he actually assumed that the energy would be h times Planck constant. And he went beyond this to propose a way to test his theory, and it was the photoelectric effect. And this is what Einstein won his Nobel Prize for, was his discovery and proof of, or the theory that would allow people to prove whether or not light was a wave or light was a particle. Already people assumed light was a wave. We had all sorts of evidence showing us that it was a wave. But the photoelectric effect, Einstein came up with a way to show that light is also a particle. I think he only won one Nobel Prize. I think so. Okay. Here's a visual representation of kind of the photoelectric effect. And the idea is something that had been around for a long time. Scientists recognized that if you shone light on a piece of metal, that metal would get charged. It would get electrically charged. And the assumption was that electrons were being knocked off. That's the photoelectric effect. Light hits metal, knocks off electrons. Pretty cool. It was either Millikan or Thomson. I can't remember who did this, but they created this apparatus. And they said, well, we could actually measure those electrons if we have a metal surface here, which is the photo surface, or the photocathode, I think it's called. And this is in a vacuum tube. It's in a vacuum tube, and you create a circuit here. And so when you shine light on the photo surface, electrons are emitted. And if there's a little bit of a potential difference, those electrons will go over to the cathode and, or the anode, the collector, we'll call it. That C stands for collector. And you'll get a current going. And it's awesome. And you can do all sorts of things with this. This is how light meters work. This is how, I think this is how like automatic door openers work. Somehow you got a little photo cell in there, and it sees you coming and changes the current, and boom, the door opens up, okay? You can. That's a great question. Why are the electrons released? And that is That is something we're going to talk about a little bit. It's a little bit what Einstein dove into. But they knew it happened. They already knew it happened. What Einstein did, though, you guys, is he came up with a way to use this apparatus to test whether or not light is a wave or light is a particle. And he said, I think it's a particle. And here's how you could prove it. He was not an experimental physicist. He was a theoretical physicist. So he came up with a theory. It took them a number of years before they actually tested it well enough to show that his theory was in fact correct. And it was using the photoelectric effect.